Thank you. I'm afraid that's a bit of a revisionist history. The truth is I was such a bad recruiter that I ended up having to do it myself. So, but I did plan on spending a few weeks helping out at Facebook, and just became so fascinated with the problem that the company was solving, what the mission of the founders were, that I've dived in headfirst, and 4.5 years later, I'm still at it. So what we're going to talk about today is some of the challenges that Facebook has faced as a, let me get this going. Some of the challenges that the company has faced as it has grown from really being a dorm room project that was started by Mark Zuckerberg and Dustin Moskovitz when they were at Harvard, to one of the largest sites on the internet today. And we're large in almost every dimension. In terms of the amount of time that people spend on Facebook, the number of interactions, the number of objects that they store, and the rate at which they view that data. So we face some very, very challenging technical obstacles, and it's forced us to redesign and re-engineer our systems at regular intervals. The growth of the site has, been amazing. And what I find to be quite interesting is that if I had given this talk 4 years ago, the graph would have looked exactly as it does now. It's only the label on the y-axis that would change, because it would have shown going from 100,000 users to 2 million users, or 2.5 million users in just record time, and that would have looked like a success story. And in fact, that's how we viewed it. So it's hard to believe that you can draw the same, the graph will show the same shape today, and really has at any point over the last 5 years. So we've also passed some very important business milestones this year. So besides having 300 million active users on Facebook, back in April we announced that the company is profitable, and we're now cash flow positive, which we've announced this quarter, which are both very significant milestones for a company that's facing very rapid growth. So Facebook is the largest social network in the US and in the UK and Canada. In fact, in Canada, it's probably one of the most popular site on the internet. But we really are a global site, and 70% of our users are outside of the US. As you can see from this picture, there's a lot more blue than yellow, and not all of it is ocean. So we have our work for us to do. Another way of sort of viewing that is we have 300 million users, and by many estimates, there's about 1.3 billion people in the world who have quality internet connectivity today. So Facebook doesn't by any means believe that our job is done. We need to provide a relevant product to the people who we're not serving today, as well as continue to create more value for those who we are. Engineering at Facebook is central to everything we do, and engineers can have just tremendous impact. In 2005, we had 2 million users, and we had 2 engineers, one of whom was our CEO, Mark Zuckerberg. And interestingly, that ratio of about 1 million users per engineer has held more or less as a constant ever since. So today, with 300 million users, we have about 230 engineers on the team. So we've even improved on that some. Compared with other companies, we believe that engineers at Facebook can simply have dramatic impact. Now, the social graph is more than just people. It's also people's connections to companies, to products, and to their friends' blog posts and photos and videos. So at the end of the day, we have a tremendous amount of data and an even larger number of relationships between data. So most of this talk, we're going to be addressing what are the challenges of storing and presenting this highly interconnected web of data. So let's start with one application we know, which is photos. Now, this is a Facebook photo album. It doesn't look that different from any other photo album you might find on the internet. In fact, we didn't think it was that different at the point we were launching photos in 2005. It's a collection of thumbnails that represent an album, and you have the ability to dive into that album and sequence through larger images. But what really made Facebook Photos different was that underlying the photos was the social web, that is the social graph. And by taking photos and tagging photos with the names of people who exist within your social graph, who are close to you on that graph, amazing things start to happen. For instance, you get an email, and the email says that somebody's taken a photo of you and uploaded it to Facebook. Very few people can get a notification like this and not look at it. It's tough. I always do. So do about 300 other million users on Facebook. So the end result is that by following these links and by exploiting the social graph, the photo application became much more relevant to people than the other dozen or so similar looking, at least outwardly looking, photo applications that existed at the time. Today, we have about 20 billion unique photos stored in 4 resolutions, so that's 80 billion objects we're storing. Well over, I think, 2 to 3 billion photos are being uploaded every month. So it's a continually growing archive. But when we launched our photo product, we certainly weren't prepared for this growth, and we didn't envision that it would be quite this popular, because at that point, I don't think we even ourselves understood the power of the graph to really drive an application. I remember that, I conservatively provisioned about 6 months worth of storage, at least what I thought was 6 months, and we blew through that in maybe a week and a half. Scrambling for more machines, more disks. It was quite a challenge, but of course, those are the great challenges to have. However, the most difficult aspect of serving this many photos is simply not storing them, but delivering them. We serve up about 600,000 unique images per second. And that is really a daunting number. That has actually driven most of the engineering effort that we've placed around serving photos. So let's take a look at how that works. Well, I said when we first started out, we didn't think the problem was quite as dramatic as it turned out to be. So, and we also were a small company, and in a small company, you can't solve every problem. And we had one engineer who was dedicated to back-end systems. And should we assign that one engineer to build a new photo storage architecture, or possibly to build a product feature that was truly unique to Facebook? And the answer there, of course, is you'll put your scarce engineering resources on building those things which are unique, and then try to buy solutions for those things that overlap with technology available in the industry. So we started using standard NFS-based file servers. We put a web server in front of them, introduced caching, and it was very easy to quickly get going. And then you start to optimize it. So we recognize that a portion of our images were viewed very frequently. And we looked at the various caching architectures that were available, but they weren't well suited for the very small objects that we were caching. So we built a new caching architecture, one based on combining Memcache with Lite. We also saw that our NFS filers were not particularly efficient, and they were doing a lot of the same metadata lookups over and over. So by building an external file handle cache, we were able to improve upon the performance of those systems. But clearly, we can do better than that. And when looking at the actual technical limitation of serving photos in high volume, what we really recognized is a disk is a disk. Whether you buy that disk in an NFS server or whether the disk is simply configured in a commodity computer, you're really limited by the number of physical I/Os that disk can perform. So the real question is, how many of those I/Os do you use in order to serve an image? And then the lower that number, the more efficient you're going to be at serving images. So when we started out just using a standard network filer, we were serving about 10, we were needing about 10 physical I/Os to serve every image. And that's because the filer had to walk down a very complex directory structure, none of which was in cache, because the caches on the filer weren't large enough to hold the hundreds of millions of images that we were needing to put on each machine. So they were not serving that application well. Through optimization techniques such as holding and remembering some of the filer metadata, setting the directory sizes to exactly match the size of a single allocation block on the filer, we were able to pull those numbers down into the range of maybe 2 to 4 physical IOs per file served. We knew we could do better. We knew the answer would be building our own file system. We built it as an overlay file system that simply aggregated lots of images into a single operating system level file so that the OS metadata cache only had to deal with a much smaller number of objects. And we just maintained a very simple manifest in memory that mapped a file ID to its offset within a meta file, and then the length of that object within the meta file. And so by building this overlay file system, we were able to deliver a constant 1 physical I/O per every image served and extend the capacity of the installed hardware platform by a factor of 4. And we call this our Haystack overlay file system, and that's technology that we've open sourced. So looking at the efficiency of Haystack, we started out at 10 physical IOs. We maybe got down to 3 through optimizations on commercial platforms, and now we're living at a constant 1. This is actually the team that built this software, and again, I've made the point that one thing I'll be mentioning today is that we are very strong believers in open source software. We make a point of contributing new infrastructure software built at Facebook to the community. We feel that not only is it an appropriate thing to do because we ourselves have benefited from open source technology that we've taken advantage of, but we also believe that that more people using it simply makes this better software. And any competitive advantage that might come by holding that technology for ourselves is certainly outweighed by the improvements in that technology that come through its broad use. So the architecture at Facebook looks pretty much like any other website, at least outwardly. You have a load balancer sitting in front of a web server, and behind those web servers you have services such as our feed service and search service, ad services, as well as a caching and database layer. So let's take a look at the web server. Our web code is all implemented in PHP. And we chose PHP for a couple reasons. Most of them have to do with the word simple. It's a very simple language. It's very easy to learn the language, a small set of statements, looks a lot like C. It's easy to write in the language because of the loose typing and the universal associative array. Very easy to read. It's very easy to debug. Probably the shortest hello world. But there's some disadvantage as well, sort of the dark side of PHP, and that comes through runtime costs. High CPU and memory consumption. It's difficult to integrate PHP with other languages. And when you get into a very large project, it doesn't support good modularity, so it encourages some sloppy coding practices. It was nice when you had 50,000 lines of code, but at 3 million lines of code, PHP becomes a significant organizational challenge. One other unique property of PHP that we learned along the way is that's one of the few languages where the new software that you write makes the old software run slower. So if you have functions A, B, and C, and now you write new functions D, E, and F, and you don't call them from A, B, and C, A, B, and C run slower than they used to. And it's simply due to the initialization cost of setting up and creating a new, more complex runtime environment at the beginning of each page request. So lots of scalability issues with PHP. We've put a lot of work into improving both the runtime performance of the existing open source PHP environment. Lazy loading, which helps avoid some of the initialization costs until you actually have proven that you need a module. Cache priming, we've made a lot of extensions to PHP, such as our cache extensions that are implemented in C. And most recently, we're working on a compiler to compile PHP to C++ and then take care of a well-engineered optimizing compiler to generate native machine binaries. And that approach shows a lot of promise. Now, many of the functions at Facebook are implemented as back-end services. And back-end services, luckily, are never implemented in PHP. The most common language is C++. But our philosophy around a service is only implement one if and only if it's required. Because a service comes with a cost. It frequently becomes another failure point. It creates complex interactions between services and other components of the architecture. But you need services because there's functions that need to encapsulate their own data, such as a search service, where it's the only effective way to deliver that functionality. And of course, it can be greatly more efficient than trying to distribute that across a single tier of servers running a scripted language. So in order to efficiently support services, we build a service framework we call Thrift. And Thrift is another project that we have contributed to the open source community. It provides an RPC environment and a service framework for easily building and deploying services. So we build our back-end services in a number of languages, all of these and some others too, and they're all connected through this common RPC that is generated through the use of the Thrift IDL. So it's a lightweight framework. Developers don't need to worry about issues of serialization and connection handling. It provides a basic server template, and we have actually multiple templates for a non-blocking server, for an asynchronous server, multi-threaded or single-threaded servers, and you just fill in your unique server functionality, and you have all the stubs that are generated for 7 or 8 different languages available for invoking that service. In addition, we found that we broke lots and lots of pieces of standard system infrastructure. So one example is syslog. Syslog is the standard Unix logging service. And when the site began to scale, it became impossible to push very large volumes of data through this logging infrastructure. We realized that we needed something that could deal with temporary outages in flows through the system. So what we built was a system called Scribe. And at each level in Scribe, for example, at an intermediate level, if there's a backlog or back pressure in the system, we'll queue log entries in memory. We'll even spool them to disk. And then when the bandwidth is available or the system interruption has been resolved, we'll funnel them through additional tiers of the architecture until eventually we're streaming the data into a single sequential log. We push a lot of data through Scribe, and Scribe itself is built on top of Thrift. We move about 12, actually, my notes are a little bit old. I checked before I left. We're running about 25 terabytes of data per day through our Scribe system. So that's at least 1,000 times more messages that are delivered by the U.S. Postal Service in a day. Of course, we don't have, barking dogs and rain, sleet, and snow to deal with. Scribe is actually remarkably efficient. It's a very small amount of hardware that's needed to support this traffic flow. Also, when you build services, you need to manage them. So part of the service framework is that somebody who creates a new service finds that it is already populated into the monitoring consoles, so it's easy for them to configure the service and to see if the service is working correctly. And all of that comes for free by using a common service framework. So what can you build with all this stuff? So let's take an example of one of our services, and the one we're looking at here is called Newsfeed. Newsfeed is a service that takes status changes and actions of our users and distributes those and then aggregates them so that other people can see all of what their friends are doing. So one of our key missions at Facebook is to make it very easy both to produce information, but also painless to consume information from all of your friends. And Newsfeed is a central part of that. So when you do something on Facebook, such as you update a status message, that information will flow into what we call a leaf node in our multi-feed architecture. When someone else looks to load their home page, they're going to make a request to one of the nodes within our newsfeed environment, which will then fan out that request across the entire tier and check to see if any of their friends, if any of the people who they're interested in have done anything new. It'll aggregate that information and return it up to the PHP layer, where we'll augment it with data out of the cache and out of our databases to produce the newsfeed story that I showed you a moment ago. And then, of course, we add the HTML and return it to the user. But the service that found the most recent set of stories and the most relevant set of stories and then deliver that back up to our web tier, that's a service implemented using the Thrift framework and managed through our service framework. So in many ways, our cache is the heart of the system. And that has a lot to do with simply the scale at which we're operating. So I'm going to spend a few moments to describe why we have such a large scaling problem. With most websites, a user interacts with that website in order to interact with their own data. When you go to Amazon, you're interacting with your previous shopping history. You also engage with some corpus of data that is shared among all users, such as the catalog, but you're actually not engaged with all of the other users' activity on the site. On most websites, typically 1% or 2% of users only 1 to 2% of the registered or active users are actually concurrent on the site at any given moment in time. So that makes this a somewhat easy problem to scale. When a user begins a session, you grab their context from disk, elevate it into RAM. You need to operate at RAM speeds for practically all interactions on the internet today because of the expectations for fast response time. And you have 1 to 2% of your user data cached in RAM. When the user stops interacting with the site, it'll simply get replaced from the cache. And the next time that they engage, that will get pulled up again. So a cache capable of holding 2% of your user's context is typically sufficient. And then it's easy to scale a system like this because Bob is interacting with his data, but Julie's interacting with her data, so we just add more servers. Those servers contain the data unique to some set of users, and you can continue to build this site out very gracefully without a lot of thought. But at Facebook, we face a somewhat more daunting problem. Users don't come to Facebook to see their own information. They're coming to find out about their friends. When the first user shows up, they're requesting data for 150 or 200 of their friends. When we have 1% of our users online, basically our entire data set is part of the working set. So this is a very different problem than almost any non-social application on the internet. And any of those of you who've worked with social applications would find probably very similar behavior in your applications. There was a point when partitioning of this information was actually pretty easy. Facebook was a college website 5 years ago. We had a UCSD site, we had a Berkeley site, we had a Stanford site, a Harvard site, and we actually had a unique database for each one of those websites. The database was called UCSD, Berkeley, and Harvard. They might be physically resident on a single machine, but they were a unique schema with a full collection of tables. And there probably wasn't anything you couldn't do with a good SQL query. If I wanted to find out which of my friends were attending an event, that would be a join between the event table and the friends table. Very easy to implement. Today, our users are a diverse group of people who have connections through all walks of life, people they used to work with, people they knew in high school, people who they members of their family. And there really is no good way of grouping this data. So we made a tough choice. I mean, we looked at all different ways of trying to find cycles in the graph and clustering within the graph. We realized that that was a very hard problem that netted very little benefit from an optimization standpoint, and we chose to randomly distribute users across databases. However, that would mean that logically, when I access my friend's data, for example, when I load a home page, that I'd be touching 100 or 200 database servers, and I can't build a scalable website if every page request is going to hit all of the back-end resources. So in order to allow this to scale, we needed a very fast cache. So you could say that we punted on the problem, because the elegant way to finesse this issue would have been to have truly found ways to cluster the data and then partially denormalize it. Instead, we chose to keep the data normalized, randomly distribute it, and then find a way to access that data at very high volumes. And the tool that we used was Memcache. This was developed by Brad Fitzpatrick when he was at Danga. He's now at Google. And we make a lot of use of Memcache. Memcache is used to shield queries from our database so that we don't end up punishing our databases when we serve a page like a home page. We also use Memcache in some very unique and very application-specific ways as well. So we get a lot of performance advantages from Memcache, but it also has its problems. It is easy to corrupt it. It's a voluntary cache. It depends upon every programmer obeying the rules. When I change data in the database, I need to delete the corresponding entries from the cache. And then the next time I read from the database, I populate the cache. Well, if anybody doesn't follow that sequence, the cache can easily become corrupted. So we've put a lot of work into Memcache. When we started deploying it, it could service about 15 to 20,000 requests per second. Today, we're serving close to 250,000 requests per second on a server. Servers have improved during that period, but a lot of this has been due to the changes we made to the core of the cache. 64-bit implementation, we improved the serialization protocols for greater efficiency. It's multi-threaded. We've modified the Ethernet drivers in Linux so that we could better distribute requests across multiple cores. Made optimizations to the network stack so that when you would call through the socket library, we would be able to batch requests for multiple requests together. So lots and lots of optimizations. This is a lovely slide. I found this in somebody else's presentation that was for a non-technical audience, but I believe it. So we're spitting out a lot of encyclopedias. I'd say the more impressive number is that we service about 120 million queries to the cache every second. So very, very high volume cache, and it really is the core of the site. One of the challenges that we face with Memcache is that it's a multicast-like protocol. When you make a request for a set of 100 or 500 keys, those requests get distributed across a large number of servers. And we've put a lot of work into optimizing that code path. So when those requests come back, they come back in about 40 microseconds, plus or minus 5 microseconds from each other. And they all meet for the first time at the switch port that's facing the client. So you make the request, and then the data comes back, and it meets right here. And that's typically the port that gets where you find buffer overrun, and then packets get dropped. So we had to figure out a way of how do we throttle these requests so that we don't keep dropping data in the network. We were finding that we had a constant 2 to 3% data loss on our network. And the way we did that was we implemented a sliding window protocol, similar to the notion of TCP windowing, but it's across multiple requests. And the variable we change, of course, is the number of requests that we're willing to make in parallel. And by doing this, we were able to cut our average request time in half, and by avoiding the data collisions. So we did this in our Memcache library. It's, again, technology that we've contributed to the open source community. But Memcache presents a lot of really interesting challenges. One of those is, how do you organize the cache? For instance, if I had a cache of large objects and a cache of small objects, that at one level may seem to make sense. But the cache of small objects may be handling a high number of requests and become CPU bound. The cache of large objects could be limited by the bandwidth of returning these very large objects back to the client and become network bound. So by mixing the two together, and I could assure that I'm going to fully utilize all of the resources on the server and run out of everything at the same time. Unfortunately, a simple rule like that doesn't apply everywhere. So we'll take this very simple example, a pool of objects, let's call them type A and type B, and we've got a pool that holds both classes of objects. And let's imagine that I'm going to make two multi-get requests for 100 keys of each type from those two pools. Well, if I've mixed those objects across the two pools, maybe because I was trying to balance processor versus bandwidth concerns, I'm going to find that my client makes two requests, and each server is going to respond to two requests of 50 keys each. Now, if I split those pools to be homogeneous pools of type A and type B, then the client still makes two requests, but each server only has to respond to one. So the service capacity of the pool has been doubled. And if I'm not bandwidth limited, then I don't care that each server is serving 100 objects back, and I've doubled the service capacity of the pool. So figuring out how to properly partition data is a complex problem. Another problem we run into, so let's just take a single pool of two nodes, both serving object type A. If I make 100 requests to the members of that pool, and each request, each server in the pool is going to serve 100 requests. But if that pool is running out of capacity and can no longer service requests because if it's out of CPU, I'm going to say, oh, I know how to solve that problem. I'll add a third machine. But lo and behold, I've done nothing. All I've done is change the number of objects returned per server from 50 to 33. Each server is still responding to the same number of service requests. And if the machines were CPU limited, then all I've done is reduce bandwidth on the Ethernet ports of those boxes, but I've actually made no improvement in service capacity. And you keep adding more machines, and you find you've worked yourself into this hole that you simply can't get out of until the number of machines is larger than the average number of objects that you're requesting from the pool. We called this the multi-get hole, and we did not discover this by reasoning this through on a theoretical basis. We found ourselves in the hole and said, I just added 5 more machines. What is going on? And did the math and realized that there was no way to work out of it. So one solution to that problem was actually to go with replication. And we'll discuss that here, which if I created 2 pools for, let's say, object type A, and each had its own unique, each one had a complete copy of the data, then I could split my requests across those pools, and in doing so, double the service capacity of my service pool, because compared to putting 4 machines, if I put 4 machines into one pool, they'd all be servicing every request. 2 machines partitioned into 2 replicated pools, each only has to do half as much work. So this is one of those things that we find to be complicated to manage because we're trying to solve a problem on multiple dimensions. It's a manual process today. We have to look at the resources of individual servers. Are they CPU bound? Are they bandwidth limited? We have to look at how we would optimize a given data set, such as the data set might fit on 5 machines. So I build a pool of 5 servers, but then I find that those 5 machines can't handle the workload. This is a tough problem. It's not a problem that's well served by a human working at a spreadsheet. It's one where some form of optimization process that looked at a trace of all of the requests to the cache, looked at all the data sizes, and then was able to calculate the appropriate grouping, the number of replicas, and the right mix of keys per server in order to get an optimal utilization of resources. Something we haven't done yet. Now, the authoritative data on Facebook is stored in a pool of MySQL servers. And we've chosen to use a shared nothing architecture. Comparing a shared nothing architecture is comparing an army of foot soldiers to a battleship. If you happen to take down the battleship, you've won the war. But a foot soldier, maybe like the poor guy in the back who's lost his head, he can be disabled, and the army keeps marching forward. So one of our core architectural principles is avoid shared architectures like the plague. Try to keep everything independent, limit your failure domains to being a very small portion of the data. Now, MySQL has been a pretty useful database for us, but interestingly, we don't take advantage of the fact that it's a relational database. We actually don't have joins in our code. We use MySQL because it has very good data integrity. It has checksums on every block. It has very good tools for validating the consistency of data within the database. And it has a pretty good administrative model. Not perfect. I say here that we've never corrupted or lost data. That's due to the software. There have been a few incidents, and they almost always involve a human touch. But we haven't had that many of those incidents because the administrative model isn't that bad. It's reasonably good. But with this many machines, occasionally somebody will get something wrong. So things we've learned about MySQL, that logical migration of data is very difficult. So we map a user to a logical database, but we put 20 of them on a single box. And 20 wasn't a bad number because a year later, those databases had grown and we only had 10 per box, so because we'd migrated 10 away. Then we migrated down to 5. And so large numbers of logical containers makes allowance for being able to allow for growth without actually having to make tough changes to how data is located, because you can map from logical to physical databases very easily. It's easier to scale CPU in the web tier, so we don't run a lot of functionality on the database servers. One of the key rules, that was a painful lesson is don't put data in central databases. Eventually, it's going to fail. Eventually, it's going to become a single point of failure. Even data that you never reference. We have hot Memcache keys that get referenced thousands of times per second, but there's only 100 of them. So somebody would say, well, I'll just put them on a central database, and then it'll never get touched because, after all those keys are in the cache. Well, if some Memcache server falls over that happens to hold one of those keys, suddenly you're hammering away at the central database, and it becomes a single point of failure. So anything that gets accessed at volume, even if you don't expect to access it, if it logically could get access, needs to be partitioned. When Facebook started out, we just had a single data center in Santa Clara. And so our web tier, our Memcache tier, and our database tier were located all in the same facility. Unfortunately, that didn't last for long. The site grew, we needed more capacity, there was no more capacity in that building, so we opened another data center in San Francisco. And we built a web and Memcache tier there. But we said, well, San Francisco's close enough to Santa Clara. We can just use a common database tier. I mean, the queries take 3-4 milliseconds from the database anyway, so adding an extra millisecond wasn't really going to hurt. But we had to address the issue of maintaining consistency between these Memcaches. So we built a Memcache proxy, and when we do a delete from the cache, the proxy actually takes care of deleting it from all copies of the cache. Later, we wanted to build an East Coast data center. And our first thought was, well, use the proxy to delete across the country. But the challenge with that was that we'd have a race condition between this proxy talking to that Memcache and the replication of the SQL statements through the MySQL replication layer. So instead, we actually put the proxy on the MySQL server itself, and we extended the MySQL language to include, to specify the keys that should be deleted from the cache. So the variant of MySQL we use includes this extension. The programmer says, make this update and dirty these keys. And at every remote data center, this happens at the same time. So the data is changed, and then the local keys are changed. All of this we give back to the community. This is all technology which is available to anyone who wants to build a competitive site today. We've consciously said that we will win when other people gain value from this software because they're going to make it stronger and better. We also could never have built Facebook without PHP, without MySQL, without Memcache. All technology that we were able to adopt from other companies, and we benefited from their decision to open source. So we've open sourced many of our projects today. Pretty much everything we think somebody would find useful. If you want to learn about any of our open source projects, we have at our developers Facebook website, we do have a page listing the open source projects with pointers to the source archives. Well, clearly we're not done. The challenges we face today are actually greater than the challenges that we faced 4 years ago. There we were trying to figure out how to add another million users. Now we're asking how do we add another 300 million users. Very serious challenges, very interesting problems in the areas of load balancing, in communication among nodes, understanding the graph and figuring out better ways to store the graph than in a relational database, because we recognize that while we've benefited from the data integrity and the convenience of MySQL, it isn't an efficient way to represent this data. Making use of the relevancy of data in the social graph in order to improve search functionality. And the list just goes on. There's so many opportunities to be able to create new infrastructure and application software that adds value to Facebook that our door is open. We're actively recruiting, and we really are looking to build our team today. In what many consider, and actually is a down economy, we've probably expanded our team by 40% this year. So couldn't help but do a little bit of a recruiting pitch since I have you all in the room. And I figured we'll, just touch on life at Facebook. So what do we do? Well, it is intense, okay? We work hard. We try to work fast. And in fact, working fast is one of our key mottos. We tell people work fast and don't be afraid to break things. We would rather that people break things occasionally, create some errors, than be so afraid of making mistakes that they work cautiously the whole year and deliver perfect code and perfect features, but only deliver a few of them or maybe never get it done. So on the way in the door, one of the first things we say is, it's okay to make mistakes. There aren't going to be any witch hunts. If you take the site down, it's not the end of your career. Move fast, don't be afraid. One of the more interesting elements of our engineering culture is what we call the hackathon. And in hackathons, we only have one real requirement, and that is you can't work on anything you're supposed to work on. If this is a project that's been assigned to you, you can't touch it during the period of the hackathon. You have to do something, hopefully something that was your idea, but other people who have interesting projects and they may need a few people to help them out on it, they'll advertise and send out notes. They're looking for somebody who would like to work with me on a project. And people use the hackathons as a way of exploring their ideas, frequently building prototypes. And these are ideas that make their way into the site. So products like our recent tagging feature and Facebook video both came out of hackathons. And at the end of a hackathon, we hold a prototype forum, and people present their projects to the company. We recently completed our 14th hackathon, which was for our first 3-day hackathon. We called it Camp Facebook, and we had people camping out on the lawn. We did this during the summer, and it was a lot of fun. We got a lot of really fantastic projects developed. So thank you very much. I appreciate your interest, and I'm certainly able to take any questions. Yes.
I have a question about network bandwidth. Hello, my name is Jürgen Schultz. I'm a researcher here at Cal IT2, and I work a lot with networks, data transfer over fast, high-speed networks. You never mentioned that the network would be a bottleneck anywhere in any of the things you do. It sounded like it's mostly the storage components. Is that accurate, or do you have anything to say about networks and where you would like that to go?
No, the network really is an issue, especially the internal network. For example, when we make multi-get requests, we're fanning those requests out to hundreds of servers. As that data flows through the network, not only do we have problems of overrun on switch ports, but we also seriously stress internal networking resources. So architectures we're looking at to do more caching of objects in the web tier will help reduce some of this, but faster networks that are able to handle spikes in traffic are very important for our ability to scale the site.
Could you please talk a little bit when you describe your logging, that you collect all the logs in the Scribe, that do you use these logs to actively monitor all the server's failures, or you just use them when something happens to diagnose? And how do you handle the large amount of data?
So the bulk of the data that we collect through Scribe, the endpoint for that data is a large Hadoop cluster. So we use that data to understand how product features are interacting with our users, or how our users are interacting with product features. Did this change impact users who, let's say, were previously high producers of content or frequent commenters, or did this change have no effect on them, but also brought up participation from users who may not have participated in the past? So we use the bulk of our log data to understand the social network and to get feedback to the development team for how the changes to our site are affecting the user community. Now, for operational monitoring, we have a separate system. We call it the operational data store, and that we use for both visualization of site data as well as alarming and active monitoring.
So you mentioned that if the A-stack file system that you use gives a one IO call and gets you the file or the object that we want. So if I upload an image over here, and assuming it goes to the Santa Clara database over here, and my friend in India or somewhere in Brazil wants to access it, do they still get the one IO coming all the way to the data center in Santa Clara, or they get a replicated data center from somewhere else where the objects are replicated? So how do you handle the wide area and also the high performance together?
So Haystack is used in our origin, and it's used to increase the scalability of the storage servers in the origin. For users who are viewing the object in a distributed around the world, very frequently those objects are being delivered from a content distribution network. And we work with multiple external partners who maintain caching servers in geographically dispersed areas. And we do that in order to improve site performance for users in those regions. So frequently, the images you see are being served from one of the CDN partners. Does that answer your question? Well, because of the large amount of images we have, we don't get as good a hit rate in the content distribution networks as might a site with a much smaller footprint. A large portion of our image references are for what we call profile photos. Those are the images that are seen on each page on Facebook. And those we do have a very high hit rate out in the CDN. And we do our best to keep those images as close to the user as possible. So Haystack provides us greater bandwidth at the origin. We replicate our origin to the east coast of the U.S. as well. We have not taken that and further replicas, bringing it overseas, but we rely on the content distribution network to cache those images used within a region locally within that region. Yes?
Kind of further touching on that, do you just have those 3 data centers, and can you talk about how many servers or anything in that information?
Anything I tell you about the number of servers will be wrong because the number is going up so frequently. Today, we have somewhere in the neighborhood of 30,000 machines. But I would actually have to make a phone call to find out the exact number because it'll be different today than it was yesterday. But it's in that ballpark. The bulk of those are web servers, and the need for those is a function of the runtime efficiency issues of PHP. The work we're doing in a compiled PHP environment, we think will give us 50 to 70% reduction in computational cost in our web tier.
Hi. It sounds like you have a lot of kind of optimization going on all at the same time, and it's kind of large scale for all this kind of optimization. How can you make sure that one optimization would not affect the others? Yeah.
You can't. And sometimes it does, and you respond to it and learn from the event. One of the optimizations, I'll give you a simple example of that. When our network was lossy, there was a period of time where we were seeing a fairly high amount of packet loss in our internal network. So we developed a dynamic round trip calculator that was used in the lowest level of our network stack. And it would figure what the average round trip inside the data center was, and then it would adjust timeouts to be just above that. Because given that there was a fairly high expectation, maybe 2-3% expectation of packet loss, setting that timeout tight allowed us to keep our latencies fairly low. Now, as our data center has expanded in its complexity and is now no longer built on a single switch, but a collection of core switches that are linked together, from the standpoint of a given client, there may be a bimodal distribution. Some of the machines they access may be 50 microseconds away, and some might be 200 microseconds away. Well, calculating a single round-trip latency no longer applies, and if one of the, let's say the one that was 200 microseconds away started to see some network latency due to congestion, that might become 250, and suddenly that single timeout value that was an average between 50 and 200 would cause us to declare timeouts for any of the requests coming from the switch that was further away inside of the network. So there's lots of cases where assumptions you will make and optimizations you make either no longer apply due to changes in network topology, or simply new optimizations end up interfering with them. And that is one of the things that keeps this very challenging. I won't pretend we always get it right. Yes?
So a lot of the work that you've done for scaling the system is around services you provide, like the newsfeed service and whatnot. But you also have a third-party developer interface that allows people to put applications on the Facebook platform. And I'm wondering, given that these people are not under your control and you don't necessarily know exactly what they're about to do, have you run into situations where a new application comes out that stresses your system in a way that you had not optimized for, and you need to scramble to deal with the popularity of a third-party application? Because
Yes.
that seems like it throws a monkey wrench into the works.
It certainly adds a layer of complexity, but the benefit of having the open application platform far outweighs the costs of having to build the infrastructure needed to protect against that type of exposure. Clearly, if you do everything yourself, then you can control it more easily than if you create a platform and expect others to build. But after we built photos and saw that we blew through our wildest estimates for success inside of weeks, and then we created an event platform, and for our event product, a few days after we launched it, was delivering more event invitations than Evite was as a company. We recognized that the social graph really did create an unfair playing field for applications. Our response to that data was not to double down the number of apps we were building. In fact, we canceled all the apps we were building. We stopped working on a calendar. We stopped working on an enhanced group application, took every developer off of it, because we recognized that we wouldn't have a lock on all the good ideas to how to exploit this capability. And even if we did, there was no way we would ever be able to build those things successfully. The number of potential opportunities there were for creating value on top of the graph. So we spent about 18 months building platform. It clearly involves risk because it means that there's external code that is using internal resources at Facebook, but we've also built the monitoring tools and put in place the operational processes to allow us to identify that, if necessary, stop something that was pathological, but generally engage with the developer and say, hey, there's a better way to do this. Let me show you a more efficient way to gather and present that information. And so far, it's been a very successful process.
What are some ideas from the last hackathon that we might see on Facebook in the future?
I think what I'll tell you is that we are launching a prototype area, and so I think that those things that have some potential of showing up on the site in the future, a number of those are showing up in our prototype. I don't know if that page has been launched yet, but it's our intent to take hackathon projects that we're not quite ready to get behind and make part of the product, and give people an opportunity to interact with them. Yes.
So you mentioned that you're using MySQL to do a lot of the integrity checks for your data, but that you don't actually use the query features to do any sort of joins across. So I'm kind of wondering how you guys structure your queries or what kind of interface you use to actually query data, any sort of relational data within your site.
Sure. The reason that we don't do joins is because the data is randomly distributed across multiple databases, so it would have to be a distributed join. Our joins really take place in external services like the search service. If I look for everybody who's a fan of Green Day, okay, I can do that in the search service, and then I can intersect that with my friends, rather than attempting to do that in the databases itself, where that would be close to an impossible problem. In some ways, we take advantage of the Memcache tier to do this as well, because the data that gets collected in Memcache is not necessarily organized in the same units that it was in the database. For example, I have a friend object in the Memcache tier that provides attributes about my friends, and that data was collected out of lots of different databases, but aggregated and effectively joined in the cache, and then can be subsequently referenced again from the cache. So both the cache and our services, such as search and feed, serve to provide that global join. And the database really is just a bit bucket. It's just a nice place to push data where you have a high likelihood of being able to read it back again. And of course, when you're operating thousands of database servers, that type of operational stability is critical. Yes.
Yeah. So I was wondering about the rate of change of the social graph. So not just like new users, but actually sort of interconnections between users, and how that affects, say, how often you run certain analytics that are used to support the day-to-day operations.
Those analytics are typically analytics that are used by the product managers and the engineering team to understand how users are behaving in the graph. So every time we change something, we're very interested in, did that make things better or worse, or did it make it both better and worse for different people? And by understanding it, we're better able to evolve the site. We do change the site a lot. And one of our, as I mentioned, one of our themes at Facebook is that we try to move fast, and when I say that we break things, we're not exclusively talking about bugs in code that cause site outages. If we also are referring to product features itself. We'd rather that somebody have an idea and get it out there, and let's find out if it's going to work, rather than spend 6 months in focus groups and in product review meetings trying to make sure that this is in fact the right product and it's guaranteed to work. Because if we did that, we'd never do anything. So we encourage people, build it, ship it, but let's really analyze it. And that's why we're pulling 25 terabytes a day of data into our Hadoop cluster every day so that we can really understand the effect of what we're doing. And if you do a bunch of things, some of them are going to be good and some of them are going to be bad. It's not, as a Monday morning quarterback, you can say, hey, we shouldn't have done these 3. But we wouldn't have done the other 10 that were successful and we wouldn't have done it in the same time frame unless we had allowed ourselves to do a few that that later we had second thoughts about and went in and refined. Yes.
Great talk. Thank you very much, Jeff. I think a lot of people in this room equate Facebook and Google as 2 of the most important sites on the internet. But interestingly, I've heard on confirmed sources that Google will spend $2 billion on infrastructure this year and has somewhere over 1 million servers spread across the world. So 2-part question. 1, do you consider that a strength or a weakness of Facebook relative to Google? And 2, if you had another 100,000 machines, would all your infrastructure problems be solved, or what would you do with those other 100,000 machines?
To the first question, Google is solving a different problem, and their deployment of infrastructure, I believe, is largely not user-facing computational resources. So it's hard for us to really compare ourselves to Google or really to anyone else. We're solving a different problem. 100,000 machines, yeah. It's really easy. Every time we have more hardware, and we're running at low utilizations, then you don't have to be as good. So you don't have to monitor as closely. You don't have to be as optimal in your understanding of each code change and how that code change affects cache utilization, the amount of data that's transferred, CPU consumed. So yeah, lots of machines is nice, but it's also not practical. We are trying to manage ourselves as a business as well, which means that we want to be efficient and make the best use of the deployed resources. Will we have 100,000 machines at some point? Inevitably. Today, I think we're doing a pretty good job with what we've got, but we also recognize there's a lot of opportunity to do better. So, as an example, our work in improving the efficiency of the runtime, reducing the amount of network traffic that's required to produce a page by doing localized caching, and those types of strategies are all things that we believe will allow us to scale the business more efficiently, make it easier to manage, and provide better performance for the users.
Is it fair to say that you're using technologies like Hadoop and Hive for more offline processing at the back end, and Memcache and MySQL for more real-time processing? And if you see a place for things like Hive and Hadoop for more real-time interactive applications?
No, Hive and Hadoop really are just for offline work. The Hive, if you're not familiar with it, it's a query generator for a MapReduce system. When we deployed Hadoop, which is the open source MapReduce framework built at Yahoo, there were about 20 people in the company who were comfortable writing Python MapReduce scripts, and they had, of course, great access to this data. We had probably another 200 people who were very familiar with SQL. So we figured, well, what does a SQL parser do? Well, it presents a schema, it accepts a query, and then generates a execution plan. So we built one for MapReduce, and for Hadoop. So Hive is our query generator for Hadoop, but it's allowed 200 people or more within the company to have easy access to our archival data, to the data resources that allow them to understand the product, understand how it's being used, and better manage products and better plan for the future. But it's nothing even close to real time. Even a simple Hive to Hadoop job, you're talking about minutes. So it really just doesn't apply to a real-time architecture. We take a lot of data out of Hadoop and then load it into database tables in our production data store and use that in order to affect how the site treats and and presents information to users. But it's not on a real-time basis. It's a batch basis, and we daily will load this information and then use it down in the sub-millisecond level.
So how do you handle funneling the data to the log data to your Hadoop cluster? Is there multiple Hadoop clusters across data centers, or is it?
No, it's one Hadoop cluster. The data Scribe is a hierarchical system, so it effectively is collecting data from a large number of machines and funneling it to a smaller number of machines, which in turn run Scribe and funnel it to an even smaller number. And eventually, you could end up with a single data pipe pushing a very, very high volume of data. And the layout of data in Hadoop is, of course, that we're distributing that information across about 1,000 Hadoop nodes. So that's sort of the end point for this log data. Yes?
So right now you have your origin database system, and you also have your East Coast database system, which presents a sort of curious consistency problem. Like, I've heard that if a user on the East Coast wants to update their profile, they are temporarily redirected to the West Coast for a duration that is at least the maximum replication time. As you move forward, do you think that you'll be looking for a different persistence model where data is local to the region?
The model will change moving forward. So the policy we have in place today that you described is correct. If a user does a write operation, a user who is typically working out of the East Coast, the load balancer actually recognizes that what URL they're referencing and ships that over to the West Coast, rather. So an East Coast user gets shipped to the West Coast. The page executes, and then we know what the replication lag is. It's typically under a second. So we wait 3 or 4 seconds, and any subsequent page request they make would be executed on the West Coast until that time limit expires, and now they're continually being presented data from the East Coast. That model is working. We're also working on different approaches to the problem where we can write data into any database, but all the data exists everywhere. So it's not as if we're partitioning the data so that some users are here and some users are there, because that itself is a really difficult problem, because you don't come to Facebook to consume your data. You're consuming everyone else's data, and some of those people would, if we did split them, some would be East Coast, some would be West Coast, some would be European. So what we envision is all the data being everywhere, but being able to accept writes at each location. And consistency, we don't need absolute consistency in our data. We need eventual consistency. If I make an update and it takes 5 seconds for that to be visible everywhere, that's really not a problem. We're not talking about a trading system where strong consistency guarantees are required globally through the system. Here, there can be some acceptable lag, and by allowing that, then you can make this a much more tractable problem. But this is definitely a part of the architecture that's undergoing evolution.
Thank you.
The replication process, does it happen each time a user makes a change in their profile or like a comment, or is it batched perhaps with other people's?
No, we try to do it as close to real time as possible. So if you make a change, that change goes to your database on the West Coast, and typically within the second, it's in the database on the East Coast. And then the East Coast database server will say, oh, it also exists in the cache. Let me clear out the old value of that value from the cache.
Should build new systems like Haystack. Like when you decide, instead of throwing more resources at the problem, you should be building a more custom storage system to handle increased load.
In terms of replacing MySQL?
No, I mean in terms of, like, for example, in the case of Haystack, at which point did you guys decide that rather than throwing more resources to handle the increased IOPS, you should be building a custom storage system instead?
That's a great question. Even before we launched the photo service, we knew what we needed. in any company, and particularly in a startup, the most important decisions are the things that you decide not to build. So I was itching to get going on a new file system because I knew that deploying these NFS servers was suboptimal. But I also knew we had one engineer, and that wouldn't be the right place to put the one back-end engineer we had at that time. A fellow named Scott Marlette, and Scott had to fix a bunch of problems with Memcache, which were needed to keep the site up, or he could prevent us, allow us to reduce the budget we were going to spend on photo storage. So it was a very clear decision. Have Scott work on Memcache and write a check to NetApp for a bunch of machines. And those are the trade-offs that you make in a resource-constrained company. So when did we decide to build Haystack? When we had one more engineer than was needed to deal with the problems of the day and ensure that the site would be up tomorrow. And at that point, we said, you're writing Haystack. And we actually kept him on the project a few months before we said, okay, we were wrong. Work on this stuff for now. And so we started and stopped the project, I think, 3 times. But eventually, we reached a level of scale that we could afford to really invest in next year's problems and not just this year's.
Are you still seeing problems with incast in your networks, or do you consider that solved by your application changes?
Yeah, that actually isn't a real issue for us today. But between improvements in the switches that we've deployed and the windowing protocol that we've implemented, we have very little incast issues. The only problem close to that, in that related space that we've run into recently, was identifying that our latency calculation was assuming a single mode in the graph, so it was assuming a unimodal distribution when in fact it's a much more complex distribution. So we have to make allowances for that in how we make those round trip time calculations. Yes.
So a couple of related questions. So not too long ago, there was a Gmail outage, and everybody on Facebook was complaining about their Gmail outage. I'm wondering if you've put any thought into, the crazy scenario where a failure at, some email provider site would in turn kind of cascade into a heavier load for your site, because a lot of people are using Facebook sort of like, a substitute for email these days. And the second part is like, can you give us any idea of like the volume of like messages that are passed back and forth over Facebook?
I don't remember that number off the top of my head. It's actually a very high number. I know we have someone in the audience here who can tell us exactly how many messages we send from Facebook. So, Tanir? A billion a day. So Tanir, who was actually the first non-founding employee at Facebook, UCSD graduate, Tanir is managing all of the outbound mail communication today. We deliver 1 billion outbound messages. Messages within Facebook, the number is actually a good bit larger than that, but I don't remember that off the top of my head. The other question you had about could an outage at Google impact Facebook? Well, clearly, you might be able to see a change in traffic, but we try to provision sufficient resources that spikes in traffic don't impact the site. So, like following the Super Bowl, a lot of people go online and talk about the game. That used to be one of those things that we'd say, okay, let's make sure that we have enough in place for, the end of the game, because we would see a pretty significant spike in traffic. Those are less of an issue for us today, as we have both a much more diverse user base and a much broader deployment of hardware. So these changes in traffic pattern have less of an impact.
You talk a little bit how you use the social graph in order to figure out, to improve the experience on Facebook, or figure out who would be likely friends and so forth. Have you guys made any effort to extract value from mining the data, the labels on the edges in the graph, what I say to other people? So kind of, an analogy is, a year ago, Google and CDC had this neat result where they were able to show outbreaks of influenza by people's search terms. You have a huge amount of content data in Facebook that represents value in that social graph, and I'm wondering what your feelings are about using that content in order to figure things out.
Well, we have a service that we've published on the site for seeing common terms that are used on the site, and you can see that as a way of tracking particular social events. And we obviously take advantage of, we try to use, the data we have in order to make the site most relevant for people. So we have engineers and whose focus is machine learning and optimization, who are trying to understand patterns in data so that Facebook is better for each person who uses it. But specifically what you're referring to, I'm pretty sure we have that as a public portal now for seeing very commonly used terms. So you can track those terms and understand whether they're part of the public consciousness or not. Okay. All right, well, thank you very much.